Hi, this is an introduction to logic. I'm Mark Thorsby, and this course overviews the basics of categorical, propositional, and predicate logic. Today we're going to actually be taking a look at propositional logic, and in particular this lesson focuses on truth tables for propositions. In essence, what we're going to talk about is what a truth table is, how to build a truth table to analyze compound propositional statements, and then we'll also talk about how to classify and compare propositional arguments. So, okay, welcome back, everyone. Let me see if I can make this a little bit bigger. Okay. So let me start off with sort of a brief review. In our last lesson here, we actually took a look at propositional. We talked about the idea that every compound statement has the property of bivalence, right? Bivalence means a proposition is either true or false. And what we did is we talked about the idea that if you create compound propositional statements, for instance, I'm just making this up, A and B, therefore C, right? There's an example. We talked about the idea that if you build a compound statement and you simultaneously know the values of each of these things, for instance, what if A is true, B is true, and C is false, right? You can actually calculate the truth value of the entire proposition by looking at what comes under the main operator. Let's see here. In this case, this is the main operator right here. So, for instance, if this is true and this is true and this is false, right? And here's where you have to just memorize it. Hopefully by this point, I'm just going to assume that you've memorized these definitions. If you haven't, you should pull out the definitions that we talked about in an earlier video, I think 6.2 or maybe 6.1. Pull that out earlier and keep it with you, right? Because remember, a conjunction here always has to be true. And then now using this value and this value and the rule for the conditional here, we can say that this statement must actually be false, right? Now, here's the problem. That's what we looked at in our last lesson, and hopefully I explained that good enough for you and that you understand that and that you did well in your exercises. But what we got to look at now is the question here of what about when we don't know the values, right? Because after all, most of the time when we hear people give arguments, if we're going to put it in propositional form, the truth is we probably don't know whether or not each exact proposition is either true or false. It may just be beyond the scope of what we can do. And so what we're going to see today here is we're going to talk about truth tables, right? And what truth tables allow us is they allow us really just this, they allow us to calculate all possible truth values, whether or not, so we don't actually have to know whether or not a specific proposition like this A, for instance, is true or false. We can calculate all possible truth values. And then looking at all possible truth values, we can actually classify specific types of statements. Some of them are always going to be bad when we classify them. Some of them are going to be good or tautological. Well, good's not the right term there, but some of them are going to be tautological. And then we can also talk about how to compare separate compound statements and sort of compare maybe what one person says compared to what another person says and see if those two arguments or those two statements ultimately end up being consistent or inconsistent or contradictory. So that's what we're going to be covering in this chapter. Now, it's interesting, truth values is something that's very interesting, and I think most people find actually that's not that difficult, and you actually probably do fairly well with it. So let me see here. Let me create a new page. You'll notice I have a new notebook thing that I'm using for our video instead of Microsoft Word. I'm hoping that it'll do better in this video than the Microsoft Word has been doing. So let me sort of go over some of the real key stuff you need to know here. Let me change the color of my pen here. So let's talk about a very important equation in terms of truth tables. You're going to see that the basic structure that we're going to do, well, let me start with the equation that you absolutely have to just memorize, and that is L equals 2 to the nth power. And what this equation tells you, it tells you how many lines how many lines a truth table needs to be in order to adequately capture all possible truth values. How many lines a truth table must be. Okay. Now, in order to actually explain all this, what I need to do is explain to you what all this stuff means, right? So L here, right, this obviously refers to the number of lines, right? 2 is the numerical. And N here, this is the important one, N refers to the number of propositional variables. And I should really say here, I could write, N refers to the number of unique propositional variables. So let me see if I can give you a little example here. Let's go back to the example I gave earlier. I said A and B implication C, right? So this was the proposition. So what you're going to see here is that first off, what is the truth table going to be? I need to first figure out how many number of lines I be. So I asked myself, how many propositional variables do I have? In this case, I have 1, 2, 3 unique propositional variables. Because for instance here, what if I added a bracket here, and then it said and B again, right? So this would say A and B, therefore C and B. In this case, I still only have 3 unique variables. So I would still need to have a 3 up here in my thing. So that means 2 to the third power, right? Is the number of lines. So what's 2 to the third power? 2 to the third power is 8, right? And that just means, so I go 2 times 2 times 2, right? And that equals 2 times 4. 2 times 2 is 4, and 4 times 2 is 8, right? So that's the number of lines I would need. Now, let me show you what that's going to look like, because ultimately, to fully get this, you're going to have to see how I do this. And let me just erase this, because this was just an example too. Right. So now remember, in terms of bivalence, so here's strictly speaking how you're going to do this. The very first variable, you're always going to write, because it's going to be very long, so I need 8 lines, right? It's going to go down here, and it's going to look like this. It's going to be true, 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 false, 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 right? And what I'm going to do, generally speaking, is, because remember, since this is 2 to the nth power, this equation will always and can only yield an even number, right? Since it's an even number, what you're going to do is for the first variable here, you're just going to say, I'm just going to go 8 divided by 2, right? And you can see here, if I just separate this, I have 4 up here and I have 4 here. Divided by 5. I'm going to put the first 4 values true, the second 4 values is false. Now, for B, I'm just going to then just divide this again. So this is going to look like true, true, false, false, true, true, false, false. So notice what I did here is I basically just divided these in half, and then I just repeated the same thing down here, right? And then what you're going to do next is when you do C, you're just going to take this and you're going to divide these in half, and your last variable will always look like this. It's just going to be true, false, true, false, true, false, true, false. So it's going to look like this. True, false, true, false, true, false, true, false. Oops. Okay? So now what I've done is I've created a table here, which actually, and I can erase this. I've created a table here where now I've listed all possible truth values, right? Because you're just gonna have to accept this at this point. Of course, we could go in, and your book does talk about why this works exactly the way it does. But that means that here on each line here, I have every possible condition for each of these propositions, because I don't know if A is true or B is true or C is true or false. But now I can see these are all the possibilities that exist, right? And the first one, of course, is where they're all true. The last one's where they're all false. And you can see here, none of these lines are ever going to look the same. Now, what's an important thing to do? Now, I mentioned, what if, for instance, if you had the B back here again, right? Let's go back to that. Let's recreate that example. So I said and erase that, and B. Now, whatever falls under the B column needs to be identical the second time around. So let's just do that here. So that's going to be true, true, false, false, true, true, false, false. Now, for those of you watching, if you're doing these exercises by hand, I actually highly, highly encourage you to use graph paper, right? Because the graph paper gives you the lines, because in a complex equation, what's going to happen is the lines could be very, very long. Because remember, L equals 2 to the nth power. What happens if you have 6 unique propositional variables? That means you're going to end up, and I'll just do the math for you, you're going to end up with a truth table that needs 64 lines. That's very, very long. And in fact, for the most part, you're never going to see those. In a later video, we'll actually talk about how to do these problems easier without having to write all these truth tables down. Okay, so essentially what you're going to do with these truth tables is you're going to build up truth tables like this. Now, what I want to do now is I'm just going to go over, I'm going to give you a couple examples here just to show you how to do it. Because you can see here, how do we go ahead and do the problem now that we've done this? And remember, always want to keep whatever falls under one needs to fall under the same unique variable identically in each case. Because if you start mixing it up, you're going to completely screw it up. And by the way, I should say this, it's very easy to make that mistake. I admit I've done it myself, and God forbid I may even do it on this video, but I hope not. So, and then what you do is you basically just run through the problem the same way we did in our last problem, except this time you just analyze it according to the definition of the rule we gave earlier. So let me get you my green one here. Maybe make it a little smaller. So, and remember, what's the rule for the conditional? Which you always want to start, just as we said, with the inside parentheses, and then you want to calculate the truth values. And it may be helpful here, just in the same way I'm using different colors, it may be helpful for you to use colored pencils, or even a highlighter might help, because you're going to see it's going to get fairly complicated. Or it looks complicated, but it's fairly simple. Okay, what's the rule for the conjunction? They both have to be true in order for it to be true. So that means that this would be true, this would be true. Any falsehood in it's false. That's going to be the basic definition. So that's false, 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 false. Actually, the pen's not doing too good here. Okay. So those ones are all false. And now what I'm going to do, that means I have to compare this line with this line, right? Because whatever falls under the main operator in the parentheses is what you're going to use. And I'm going to compare these two using the conditional rule here, right? So then I'm just going to look at it. And here I would encourage you to use both your fingers if you're doing it by hand, right? So that's going to be true to true. Remember, what was the rule for the conditional? The rule for the conditional was that it's always true unless you start with truth and the consequent is false. So that means this is, oops, why did I do that? Okay. So that means this is true, false, true, 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 true. Now some of you are saying, how did I know that those are true so quick? Remember, the only time in which it's going to be false is if the antecedent is true and the consequent is false. In all of these cases, the antecedent is false, which tells me it just has to be true. Okay, now that I've done what falls under that main operator, now I need to go to within the brackets here, then I would move to the actual main operator, which is this guy right here. And usually when I do the final main operator, I'll just do it right here. So, and the conditional rule, again, the conjunction rule is that they both have to be true. You know what, let's actually use red here just to signify we're doing the main operator. So that's going to be true, false, 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 true, true, false, false. Now, typically what you're supposed to want you to do is then, I'm using a different color here so you can see what falls under the main operator, but you can also square it, or I actually prefer to highlight it if I have a highlighter. And now we see that these are the possible conditions in which this statement, this entire statement, would be how we would analyze it, right? So that means that this statement would be true if these conditions existed. right? It would be false under these conditions. It would be true under these conditions. And it would be false for these conditions. So that means that this statement is true here, here, and here. There's 3 cases in which this statement can be true. One in which A, B, and C are all counted as true. Another one in which A is false, but B and C are true. And then it's also possible if everything's false, but B happens to be true, then actually the statement's still true. Sort of interesting. And we're not starting with an ordinary language example here. We'll look at that in the homework. But you can see here, now that if, say for instance, I read an argument, I did the truth table. Now, in order to know if the statement was true, I actually just need to investigate whether or not really B is true. Because if B is true, then B has to be true in each of these cases. And in this case, only B has to be true in order for the whole statement to be true, right? That means I can actually just really limit what I have to go research and find out whether or not something is true given that statement. So I hope that makes sense in terms of the way I did this. I feel like sort of when you teach and talk about these truth tables, you sort of just jump in the deep water and learn to swim. And we'll just do example after example here so you get a sense of it, okay? So let's do another example here. Or let's actually write down what the basic steps are for doing a truth table. The first step again was to determine the number of lines. Right? You need to make sure to determine the number of lines you have to put in your truth table. 2, make sure you consistently what's the word I want to say? You consistently record the truth table. Right? And when I say consistently record it, what I mean is make sure that whatever falls under one variable always is the same as what falls under the next variable. And again, utilize that system of the very first variable, you're just going to divide it in half. The first half is going to be true. The second half is false. The second variable is going to divide again. And you'll do that on and on until eventually your last variable should just be true, false, true, false, true, false. And that's essentially the process for creating this. So make sure you consistently write that down. Because if you're not consistent, you'll get it wrong. And that's really critical, actually. And then once you've done that, then you're going to compute the table using the truth functional rules. So let me do another example here. Let's see here. Let's say we have this, and I'll pull these from your book, actually. Let's say we have this example. C and not D, therefore E. I'm sorry, then E. And I don't know, this could be, for instance, Charlie's going to the party and Derek's not going to the party. If Charlie goes to the party and Derek does not go to the party, then Edward will go to the party, right? So the question here is, under what conditions would this statement actually be true, or in what way would we say whoever said that statement would be a liar, for instance? So the first thing I'm going to do, just to use the steps here, is add 3 unique variables. So that means how long does my truth table have to be, right? And don't be afraid just to write it again. L equals 2n, 3, 8. So I need 8 lines long. And so I'm going to take that first variable here, and I'm just going to write true, false, true, false. By the way, I apologize. I've got a cold right now, so this video probably doesn't sound too good. So that's going to be true, 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 false, 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 false. Right? Now the first thing, and then the next thing is, we want to make sure it's consistent, so I look at, are there any more C's? No, it's only C. So then the D here, I'm just going to divide that in half. So that's going to be true, true, false, false, true, true, false, false. And then E is just going to be true, false, true, false. Now it's important here to actually be really careful in terms of how you write this out, and that's why I encourage you to use graph paper. because you want to make sure that when you compare them, it's not like crooked. So you don't want to compare this, this, and this. You want to make sure that everything's on the same line. Okay, so where do I start from here? What's the first operator I should start with? I hope you see it. I should start with the negation here. Right? Always start with the negation because the negation only depends on one thing. A negation in the parentheses. So I start with what's in the parentheses, start with the negation. What's the rule for negation? Well, if this is true, this is going to be false, false, true, true, false, false, true, true. And then next I'm going to use this one here, right? Which is going to be, now remember, I'm going to only compare this and this. Now, once I fill in the negation value, I don't have to worry about this. I can ignore it. And it may even help you just to sort of exit out to make sure you don't miscompare them, right? And remember, the conjunction rule says they both have to be true, otherwise it's false. So that means that this is false, false, true, true, false, 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 right? And now this is the main operator in the parentheses, which means I'm going to be comparing this line and this line using this conditional rule here, okay? And I'm going to change the color here. You may not be able to do that, just so we can know that this is the final line that actually helps us determine under what conditions this compound statement would be true. So the conditional, right, anytime it has to be true and then false, and that's going to be false. So that means that this is true, right? False and false is true. True and true is true. True, false, right? That's false. And then the rest of these, since all of these are false, is going to be all true. Right? And then I usually box it so that way you know what to look at. Okay? Now, so this is essentially how we do it. As you can see that this statement is actually always true. There's only one case in which this statement would be considered a lie, and that would be a case in which C was true, D was false, and E was false. If those things were all happening, then this statement would be false. Otherwise, it tends to be true. So you can imagine that this statement has a high probability of being true, obviously. Of course, in order to actually know it's true, we'd have to go into the world, right? And check it out and all know what the propositions themselves are. But this is essentially how you build the truth tables. And I'm not going to do too many more examples like this because I think that you can see how to do it. And you have to take a look at your book, and also have other videos that are posted on the YouTube channel you can take a look at. So what I want to focus on now is how do we classify statements? Once I get all of these together, what kinds of possibilities exist in terms of classifying types of statements? So let's move here to the next page and take a look at that. Okay, so what we're going to be looking here is classifying statements. Okay, classified statements. So there are really three types of statements. The first is what we call a tautology. And that's when all of the values are true. And when I say all values that fall under that main operator, not all of the other values, but all of the main operator values. Number two, another example here, if you don't, besides a tautology, you can have a self-contradictory statement. Right, a contradiction, essentially, and that's when you have all false values that fall under the main operator. So for instance, this of course would be the worst sort of statement because that would mean that in all possible statements, in all possible conditions, that whatever statement is self-contradictory is always bad. It's always false. So you always want to obviously avoid those. And of course, the majority are what we call contingent. And basically that means that you have mixed values. You have at least one true and one false value that falls under the main operator. Okay, so you can see here if we go back to our page we were looking at earlier, if you go back here, what kind of statement was this? Well, it almost was a tautology, right? Because they're all true, but it's not. It had one false, which means this was, if we're going to classify this statement, we would say that this statement is contingent. It's contingent upon, well, really, this line, okay? Similarly, if you go back to our, I think what was our other page, right? This was true, false, true, false. This is also contingent. The grand majority of all of these are actually going to be contingent statements. So let's see. Let me give you an example here. Let me actually show you the book here. And because this is easier for me just to show you instead of me doing all the truth tables. One of the things you'll find in this chapter 6.3 is that it actually takes a while to do all this stuff, to run these truth tables, especially if they have more than 3. Especially if they have 4 or 5 variables, it takes a long time. Generally speaking, your book is never going to ask you to do more than 16 lines at any one time. But here's the basic definition again. A truth table gives the truth value of a compound proposition for every possible truth value of its simple components. Each line in the truth table represents one such possible arrangement of values. You can see here, 6 lines is 64. I'm sorry, number of different simple propositions. I think it's easier just to say unique variables because that's easier for me to remember than the way they sort of word this. The wording is sort of odd. So let's scroll down here and take a look at some of the examples that Hurley gives in terms of this. You can see one of the things that Hurley's going to do. I don't think it's necessary to do, but it may be helpful to do for some of you just to get used to it, is to write the A and the B separately and then to fill them out. Because you can see here, here's a B. The B comes up multiple times. So it may be helpful to do it, to write them out here so that then you can just sort of write them in real quick without having to think it through. I don't usually do that because it's sort of just extra writing and it doesn't seem necessary. But it is probably helpful for people who are just learning how to do this. Okay, you can see he does the same thing. Since this is the main operator, this is what follows. This is the truth values we're going to look at. If you classify this statement, right, it's contingent. Okay, so let's take a look at here. Again, all true, all false, and then contingent. You can see here, here's a tautology here, right? And let's see how to say. If George goes to the party, then Harry's going to go, and George is going to go, then Harry is going to go, right? If I make that claim, that's true under every possible conditions. Ironically, even if it's false that George is going to the party and Harry is going, that statement is still true, right? This is what we call a tautology. One of the things that's interesting too philosophically about tautologies is tautologies never really tell you anything, because if you make a statement that in every possible condition is always true, that doesn't really tell you anything new about anything, right? So you have to be really careful about tautologies, because even just because we're saying that tautology is always true under all possible conditions, it's actually pointless then. Because if it's always true, then that doesn't really tell you anything, right? Especially if George and Harry aren't going to the party, that statement is sort of meaningless. And similarly, self-contradictory statements are obviously bad in another way, right? This is an example here. Either George is going to the party or Harry is going, if and only if it's not the case that George goes and it's not the case that Harry goes, right? Now, you can imagine we don't usually talk like that, but if someone actually gave you an argument like that, it would be very difficult to know if what they're saying makes any sense. And herein lies the value of propositional logic. Because you can see that when you actually run through the truth table and you figure out what falls under the main operator, you see that under every condition, this statement is false. If it's false under every condition, then it's totally contradictory and totally meaningless. I mean, this at least has meaning. This has no meaning. It doesn't even make sense. It's nonsensical. So this is necessarily true, and this is necessarily false, right? Okay. Now, let's talk about comparing statements. Comparing statements. I guess I'll move over here to the next page of the little booklet I have here. What if we're going to compare? Now, we should mention here that when we're comparing statements, we're only talking about comparing two statements, two compound statements. Also about two compounds. We're not talking about comparing 3 and 4 and 5 statements. We're mainly only talking about comparing two types of statements in particular. Now there's 4 possibilities. I'll just write them over here. The first possibility here is that the 2 statements are logically equivalent. Oops, I misspelled that. Let me erase this. That's one of the reasons I'm using this little book here, because I can use my eraser on this thing. Logically equivalent. And what this means is that the values that fall under the main operators in each statement are identical. They have identical values. So, oops. I was hoping that this new book thing would help my handwriting. Unfortunately, it's not. So let's give you an example here. Logically equivalent statements, for each line, they have the same value. So take a look at this one. You have K then L, and then you have not L, therefore not K, right? So the first line here, and you can see why it's so important to label everything consistently. So see how the K here is true, true, false, false? And see how this K is true, true, false, false? Make sure to label everything correctly, because I guarantee you, someone who's watching this video, and when you take your test, you're going to make that mistake, and then you're going to get the wrong answer. And I want to warn you not to do that. So you can see here, but if you label everything correctly when you compare them, and you can also see you can only compare statements that have the same number of values and the same values too. So we're talking about 2 statements with the same values. So on the first line, this is true and this is true. On the second line, this is false and this is false. And then on these other 2 lines, it's true and true. And then over here, it's true and true. Which means that these statements are logically equivalent. And that's actually, we're not going to talk too much about it in this video. But later on, that's going to become fairly important, because that means that you can actually replace this statement with this statement. These statements effectively have the same truth functional meaning. Not the same meaning per se, but in terms of truth functionality, they're the same. Okay, and that's really key. So the first one here is logical equivalency. If something's logically equivalent, both statements that you compare have identical values. And I'm going to add this over here. We're talking about 2 compound statements, each with the same number of variables. And the same variables too. Okay, so I should add that in terms of what kind of statements you can compare here. So the first one here is statements that are logically equivalent. The second possibility are statements that are contradictory. And a statement is contradictory if on each line the statements have opposite truth values. Right? It's contradictory if it has opposite truth values on each of those lines. So let's take a look here at Hurley's book here to see what he gives you an example of. Let's see if I can make it a little bit bigger for you. Okay. So notice here, so we have 2 statements, each with the same variables and the same number of variables, 2, K and L. Right? Let's take a look at it. When in this statement, K, the statement is true, but in this statement it's false. In this one it's false, and this one is true. And this one is true, and this one is false. And then this one is true, and this one is false. See how they're opposites? Now, if they're opposites, that means that wherever this statement exists, this statement will be false. And under the conditions where this statement is true, this statement will always be false. So which means that these 2 statements are contradictory. Now, here we should maybe identify the really principal law in logic. It's actually called the law of non-contradiction. I think I've even mentioned this in an earlier video. The law of non-contradiction says that something cannot both be and not be at the same time in the same way and in the same respect. And this comes from Aristotle. Now, what that means is that we should never ever argue in contradictions, right? Because if we make contradictions, that means we're saying something is and is not at the same time. Because think, imagine you're talking to someone and they say, if you kill bats, then the lice problem will be solved, right? And then they go on and they say, and I also believe that if you kill bats, and the lice problem will not be solved, right? You can't believe both things simultaneously. So contradiction is sort of the mortal sin in philosophy. And when you compare statements that are contradictory, you should automatically know that whoever's making those assertions does probably know that they're making a contradiction, but that whatever they're saying just doesn't make any sense. So contradictions are really important to understand and spot. So you can when you compare statements, you may discover that they're contradictory. Okay. So that's the second type of possibility in terms of second category for when we compare statements. What's the third possibility here? The third possibility is that they're consistent. And consistent means there's at least one line where both statements are true. There's at least one line where both statements are true, right? All you need is one. And that's what it means to say that statements are consistent. If you're here, for this example, imagine, for instance, that you're a police investigator. For all I know, maybe a police investigator is watching this video. What does it mean to say that two witnesses have consistent statements, right? Two witnesses will have consistent statements if there's at least one line in each of their statements, the same line in which both of their statements ends up being true in the main operator. So let's take a look here at the example. And here I hope just showing you these examples in the book help rather than me writing all this out. Otherwise the video would be very long, right? Okay, so consistent here. So the first line here is true and true, right? And notice these are all false and these are all false, right? So this is consistent because of this first line, right? So true and true, that automatically means that these statements are consistent. This is true and this is false. This is true and this is false. And then we have false and false. Something that's very important here is do not think that simply because the last line here is false and false that they're consistent, right? It has to be consistent in terms of truth, not in terms of truth functionality, not in terms of the non-functionality of it, right? So you need truth here. Just because you have a line where they're false doesn't mean anything, right? What they need to be here is you need one line that's true, okay? Now, what's the last one? The last possibility, if they're not consistent, is that the two statements are, let me erase that, are inconsistent. So that's the fourth possibility. That they're inconsistent. And inconsistent means there's no line. Now remember, the same line. There's no line where both statements are true. My chicken scratch here. It was horrible. Okay, I hope you can read it. But that's why you have a book, right? So let's give an example here of something that's inconsistent. Notice that in this statement, we have both truth and falsity, right? And over here, we both have falsity and truth. So both of them have bivalent properties, right? It's possible for each of these statements to be true. But we'll see it is not possible for them to both be true at the same time. Hence, they're inconsistent. So for instance, where this is true, this is false. Where this is false, this is true. Where this is false, this is false, and where this is true, this is false, right? Notice that they're not logical contradictions because there is a line at which both of them could be false simultaneously. So they're not contradictory, they're not opposites, right? But there's no line in which truth always the same for both of them, which means it's inconsistent, right? Whereas Hurley says there's no line in the cause of the main operator where truth values are both true, right? And this is important because one of the things I've noticed is that oftentimes students accidentally make the mistake, both in terms of consistency and inconsistency, of thinking that if there's a line where they're both false, it's consistent. That's not the case. It has to be truth. And simultaneously, people can get this mixed up because, right, here this was true and this was false. This was true and this was false. And this is false and this is true. You might think that they're logically contradictory. They're not because of this third line. Okay, so that is essentially how you classify and compare statements. Let's do a sort of quick review here to remind everyone, right? What are the possibilities? When you classify statements, you can either get a tautology a contradiction, a self-contradictory statement, or you can get a contingent statement, right? And then when you compare statements, right, you can get a logically equivalence, contradiction, consistency, or inconsistency, right? Now, I like that example with the detective because you can see here why consistent and inconsistent is important. And now maybe when next time you watch one of these like CSI or one of these like shows, detective shows, and you hear someone say, the witness's statements are inconsistent. Now you know exactly what inconsistency means. Inconsistency means that both of them could be lying, right? But there's no case in which they're both telling the truth, right? That's inconsistency. Consistency means they could both be lying, but there is a possibility that they're both telling the truth. Contradictory means one of them is true and one of them is false. Logically equivalent would mean they both have the same story, if you will. And that might hopefully help you in terms of thinking about these things. So what should we do now? Maybe let me just take a look at your homework and show you what your homework is going to ask you to do. So let's go over here to the Hurley textbook. Let me make it a little smaller for you. Okay, so here's the exercise of this, right? So first thing I'm going to say is use truth tables to determine whether the following symbolized statements are tautologies, self-contradictions, or contingent statements. Now, I can tell you this one, and, therefore, and, therefore, and, therefore, and. What do you think that's going to be? Well, maybe we should do the problem real fast, and we can actually see what it is, right? So let's do that problem. Let's see if I can make it big here. Okay, so how do we do this? Now, this one's easy. The first thing that we do here is ask, well, how many lines in our truth table? Remember, here's our equation. L equals 2 to the nth power, right? In this case, I have 1. 2 times itself is 2. So that means if this is really easy, right? This is going to be true, false, true, false, true, false. Okay? And now always start with the internal operators first. If this is true and this is true, that's true. This is true and this is true, that's true. And then and now I'm going to compare this line and this line using this rule, because this is the main operator. You can see here why I spent time talking about it both of the last two videos, why it's important to know what the main operator is. If this is true and this is true, well, it's true. If this is false and this is true, it's true, right? And you can exit out here, right? This is a tautology. This is the tautology. And I hope you saw that it was a tautology, actually, because think about it. Imagine if I said this. If Nick goes to the party, then it's the case that if Nick goes to the party, Nick's going to go to the party, right? All of that can be just sort of simplified to say, I guess Nick's going to the party, right? So that's a tautology. And then they're going to ask, don't think necessarily this is a tautology just because it looks the same. So we could do that one and we can show you what it is. But you can see this is how it's going to work. These first two are easy because these are 2 lines you're going to need. This one you're going to need 4 lines because you've got an S and an R, right? So that's going to be 4 lines. E and F, 4 lines. H and K, 4 lines. MP, 4 lines. ZX, 4 lines. You can see mainly they're going to give you 4 lines. Oh, number 9 is where it kicks in. It gets a little harder. Because here you have 3 variables. You can see now you're going to need 8 lines. And then you can skip all the way down here. What about this last one? You've got F, E, G, H. You got 4 unique variables. Right? Am I missing one? No, yeah. You got 4 unique variables. So that means your table is going to be 16 lines long. You can see that they're not going to usually ask you to do anything more than 16 because then it just becomes crazy unwieldy, right? Okay, so now what do you got to do in section 2? Use the truth table to determine whether the following pair of symbolized statements are logically equivalent, contradictory, consistent, or inconsistent. First, determine whether the pairs are logically equivalent or contradictory. Then, if these relations don't apply, determine if they're consistent or inconsistent. So let me just do one of these problems just so you can see how to do it here. Maybe a little bit of a longer one. Let's see here. Let's snip. Let's do this problem here. Okay, so let's do this problem. So the first thing, of course, to recognize is ask yourself, how many lines does this thing need to be, right? A and X, so I've got 4 variables. L equals 2 to the, 2 to the second, right? So that means it's going to be 4 lines long. So I'm going to go true, true, false, false. right? And then the X, well, once I do the A, just go ahead and fill in the A's for the other ones. This is going to be important, especially because if you start having to do these kinds of problems on your tests, if you're going to take a test, this is where you're liable to make a mistake. Just go ahead and fill it all in, get it in there, so that way you know that you're comparing the statements correctly. Because notice this one's sort of tricky, because if you did this first, you might start over here and say this is true, true, false, false, and just mix them up. So then the X here is going to be true, false, true, false, true, false, true, false, true, false, true, false. Okay. So now let's start with this one, and then we'll sort of work our way through it. So if here, maybe I'll change the colors here. So that means this is going to be false, false, true, true. Now I'm going to compare this and this using this rule, the biconditional rule. We haven't used the biconditionals too much in the videos. What's the rule for the biconditional? They both have to have the same value in order to be true. Otherwise, they're false. So if there's different values, they're false. This is false and this is true, so that means this must be false. False and false means it's true, ironically. True and true means it's true. And then true and false means that it's what? It's false. Okay? And so I'm not going to exit because let me make that a little clearer. Okay? So remember, because this is what I'm going to be using, this line, since it's the main operator, is what I'm using to compare to this statement. So let's go then fill in this statement and see what we get. Now you can see here I have two parentheses, so I need to do both of these parentheses before I can get to the main operator here. So that means this is going to be false, false, true, true. And then I need that conjunction rule. That's that. It's a real strict rule. Everything's got to be true. That's false, false, true, and false. Okay? And then over here, let's do these. So that's going to be false, true, false, true. And then I get that conditional again. So that's false, true, false, false. I'm going to switch to red. Now I'm going to do this main operator. And remember, what's the rule for the disjunction? Remember, that means or. So this says X and not A, or A and not X. The rule is that one of them has to be true. That's all. Otherwise, it's false. So if they're both false, it's false. So what am I comparing here? I'm going to compare the main operator in each of these parentheses, which is this line, this column and this column. So that means that false and false is false. False and true is true. True and false is true. Then false and false is false. Okay, so now that I've done this, you can see here I could classify these statements. Both of them are contingent, because you can see they both have true and false values. So now let's compare them on each line. Where this was false, this was false. Where this was true, this was true. Where this is true, this is true. And where this is false, this is false. If they have identical values, right, go back to our notes here. Identical values means what? Right? Identical values means they're logically equivalent. So I would just say this is logically equivalent. Right? And that's how you do the problems. You can see here you have to make sure your handwriting is neat. What I encourage you to do is get a highlighter, because when you compare these, especially when they're long, and highlight the columns that fall under the main operators. So that way when you compare, it's easy for you to see, and you don't get too confused. You can see using different colors is also helpful. I've had students use colored pencils and things like that. Generally speaking, I say a highlighter is all you probably really need, and maybe graph paper. But that's how you do these problems, okay? It's really not too difficult if you understand the basic mechanics and you just work slowly, right? Okay, now here you can see that they had the same number of they have the same number of unique variables, but they have more variables here. And then finally, it's going to ask you to use truth tables to the answers to the following exercises. So Here's what you got. Renowned economist Harold Carlson makes the following prediction. The balance of payments will decrease if and only if interest rates remain steady. However, it is not the case that either interest rates will not remain steady or the balance of payments will decrease. What can we say about Carlson's prediction? You can see here, like when you first hear that, you're like, I'm not sure. It sounds fairly confusing. But actually, if you go through and you take what's in the parentheses here and you put it into propositional form, right? And you can see here, this is just one statement, so we're not comparing statements. We just want to figure out if it's a tautology, if it's a contradiction, or if it's contingent. So you just basically, to do this problem, you basically write out the translation, perform the truth table, and then once you perform the truth table, you just need to classify the statement. And then later on, there's other ones where you have to compare what Dr. Frank says to Dr. Harris, so then you're going to compare the statements and so forth. But I really like how in these problems you actually get a sense for how logic here is fairly helpful here in analyzing all of this stuff. So that is 6.3 truth tables, and you're going to see some of you are probably thinking, well, wait a second, what happens if I have 10 variables? What do I do? Obviously, it seems like you need a computer to calculate that many. Or at least a huge piece of paper. And that's what we're going to work on in our next video, is we're going to look at in our next video we're going to look at truth tables for arguments, not just statements, and then we'll look at in the 6.5 here on what's the shortcut if you have lots and lots of variables. So that's what we got coming up in our next videos. So that's truth tables for propositions. Thanks for watching, and I look forward to seeing you guys online. Bye.